Hello everybody, I will start my today's another coding practice. So today I will solve this question, k crosses point to origin. So in this question, I will be given an array of points and also integer k, and I will return the k crosses point to origin 0, 0. The distance between 2 points on the xy plane is the Euclidean distance. So I will use the Euclidean distance for calculating the distance in this question. And I may return the answer in any order. Good. The answer is guaranteed to be unique, except for the orders that it is in. Okay. So the question seems to be quite, straightforward. So I will be given the recent point, and for each point, I will calculate the Euclidean distance from the origin. Then I will find the k, smallest points whose distance, in terms of the distance to origin. Then I will return the top k points in the list. And I don't have to sort all those k points. The order of the points in the returned array doesn't matter. Yep. And also I will clarify that k is less than or equal to length of the point, number of the points. So I can always find exactly k processed points to be returned. There are enough points. And also, as the question statement suggests, the answer is guaranteed to be unique. So this means that, for example, if k is 3, and I try to find the top 3 smallest points, it is possible that top 1 and top 2 are tied in terms of the distance to origin. However, the third point and fourth point, for these points, the distance from the origin must not be same. Because it's the same, the third point and the fourth point are the tie, so I cannot determine the answer, in a unique way. So that's one more thing I'd like to clarify, before working on this question. Okay, so that being said, let me get started. So in this video, I will introduce 4 algorithms. The first algorithm is sorting. The second algorithm is using the MaxHeap of size k. And the third approach I will introduce is QuickSelect. And fourth approach I will introduce will be the CountingSort. CountingSort. Yep, so I will introduce these 4 algorithms in this video. So please look forward to it. Okay, so let me start with the sorting algorithm. So this is the most intuitive algorithm I can use. So basically, I just have to sort the points in ascending order in terms of the distance to origin. Then I will return the top k, first k element in the sorted list. Yep, so I want to implement it. Okay, so in this way, in line 11, I sorted the points and I specified the key as the lambda function, kind of callback function, which calculates the distance to the origin from the point, tuple, coordinate tuple. Yep. And then in line 12, I return the first k element in ascending ordered point. Good. I will submit it. Okay, so for this sorting algorithm, time complexity should be, assuming that the number point is n, the time complexity should be n log n for sorting. And for the space complexity, it should be O of n. This is needed to, do the sorting in line 13. In Python standard library, sort method, sort algorithm uses the TimSort. And TimSort, in my understanding, uses the O of n extra space. So that's the space complexity. Okay, so now I will introduce the second approach. Okay, so in this approach, I will take a look at each point and calculate the distance. And also, I will use the heap, MaxHeap, on my hand. So every time I see the new point in the traversal, I push it into the heap. This is a MaxHeap. Then, if the, according to the distance, MaxHeap, I, I will pop the elements from the MaxHeap. If the size of the heaps is k plus 1. So every time the size of the max heap exceeds k, the element is popped out. So the heap size is always k. And the thing is that every time I pop out the element from the heap, it is the maximum. The point with the maximum size from the origin in the heap. So I can always keep k smallest point in terms of the distance in the heap. In the end, I just have to return the point in the heap. So that's how it works. Okay. So that being said, let me implement this. So this distance is actually the square of the distance. Yeah. And I will push this element into the heap. In this way. So, yep. And one thing I'd like to clarify is that I use the Python libraries heap.q.heap push and also later heap.q.heap pop. And this treats the internal list, in this case heap list, and it works as if it is the mini heap. So, and there is no option to make it work as the max heap. So as the workaround, I push the element. When I push the element as a tuple, I negate. I multiply -1. -1 to the distance square. So in this way, when I try to pop it out, always minus distance square is the smallest one. That one should be popped out, which means that the distance square, element with the max distance square should be popped at first. So it works exactly as I wanted. So I do it in this way. Okay. Oh, sorry. Okay, so in this way, after the iteration, it is guaranteed that there are exactly k elements in the heap because we have more than or equal to k points in total. So I will return this point in this way. So each element of the heap is now the tuple of distance x coordinate, y coordinate. But I'd like to, include only x distance, x coordinate and y coordinate. So I do this conversion. Okay. So now I'm pretty confident on my code. So let me run it. Oh, I have to comment the first one out. Good, and never submitted. Okay, accepted. So now I introduce the third approach, which is the QuickSelect. So, oh, sorry. I will quickly tell the complexity analysis of the second approach. So in the second approach, the time complexity should be n log k, because in line 21, I iterate for each point. So it should be n steps. And in line 23 and 25, I do the push operation and pop operation into the heap. And heap, push and pop operation, each of them takes O of log k, assuming that the number of elements in the heap is k. Yeah. So in our case, the size of the heap is up to k. So it should be log k inside of this for loop. So in total, it should take n log k time. And for space complexity, it should take O of k for heap. So in this heap, as I said, there are up to k elements. So the time complexity should be O of k. Okay, now I start the implementation of QuickSelect. So in the QuickSelect approach, basically what I will do is, the QuickSelect is a kind of combination of recursion and partitioning. So I will do the partitioning recursively in QuickSelect. So firstly, I will tell you what the quick partitioning is. Let me think of this kind of array, this array. And when I do the partitioning with partition pivot number, say 9, I will mutate the array. And in the end, it should be something like this. Okay, let me do the pivot number as 7. So this is a pivot number. And what happens is that only for the pivot number, it should be put as the position where it should be after the sorting. So that's the pivot number's position eventually. And all the elements which is greater than the pivot number should be greater or equal to the pivot number. And every number before the pivot number should be less than pivot number. So this is exactly what I will do with the partitioning. Yeah. And the good thing here is that my task is to find the k smallest elements. So let me let's think that these are distances. And even though it is not displayed here, let's think that each element also has x and y coordinate as the tuple so that I can restore xy coordinate from the sorted distances. And what I mean to say do from now is imagine that the k I'm looking for is exactly at this pivot number's index, or maybe -1. Yeah, because yeah, it's the first element. Yeah. Okay. So let me think. Yeah. So this is 3, 4, 5, 6, 7, 8, 9. This is index 9. So okay, I will assume that I'm looking for the 10 smallest closest points. In that case, if the pivot number is by chance here, I just have to return all the element before. Yeah. But if the index, what I'm looking for, is like 5, and if it is before the pivot number's index, then I still have to do that kind of partitioning inside of this first half, because in this first half, the point which is larger than the exactly, I forgot which index, but index 7, which I'm looking for, is included. So I can say 8th or 9th largest element point is included somewhere in the first half. I have to, yeah. That means that I can't just return the first 7 element. So I do the partitioning again in the first half. Then by chance, if index 7 is chosen as the pivot numbers index, then I just have to return the elements before, I mean, yeah, including the pivot number index and numbers before. And by chance, if I pick select the pivot number index, which is larger than I is 9, then I will do the partitioning in the latter half. And I will keep doing until, by chance, pivot numbers index is exactly the k -1, which I'm looking for. So I do that recursively. So that's what I meant to say by the word recursive partitioning. Okay, so that being said, let me start the implementation. So in line 39, this is the list of distance, list of tuple, and each tuple is distance x coordinate, y coordinate. I will mutate this distance array so that first k elements are exactly the first k points, which are closest to the origin. But I don't have to care the order of those k elements. Okay. So as I showed before, I do the partitioning to the specific range inside of this distance list. So I specify the range low and high as the argument of partition method. Yep. Then I do the partitioning, and after that, I just have to return the first k element. And as I just like before, I have to return only x coordinate, y coordinate. I do something like this. Okay. So now my remaining task is to implement the partitioning. So for this partitioning, let me assume okay, so let me assume that yep, 5 is the pivot number. I picked the last element as the pivot index and pivot number. And I will take a look at index, and this is row, and this is high, which is equal to p. I will take a look at index row to high minus 1, and I will traverse it with reader pointer. And if reader number is smaller than the pivot number 5, I will swap writer and reader numbers in this way, this and this. Then I will increment the writer pointer index because I don't want to overwrite this here. I just want to keep smaller numbers who were smaller than the pivot number in the range before writer pointer. And now I move my pointer to, now my reader pointer is 6, which is larger than pivot number 5, which is okay. And reader is now 5. This is the same, so I don't have to move it. And now reader is 2, so I swap reader and writer. Then increment the writer pointer. So in this way, every number which is before the writer pointer is, smaller than the pivot number. Now, if I swap writer number and pivot number, so in this case, there's the same by chance, but after swapping it, so this writer pointer is actually the eventual pivot index. Yep. So I can see every number which is smaller than the pivot number is before the pivot, eventual pivot index. And every number which is larger or equal to the pivot number are after the eventual pivot index. Okay, so I will implement this. So in this way, I calculate the reader distance. And if reader's distance is smaller than the pivot numbers distance. Then I swap reader and writer. So let me just say R and W. This is a bit, too wrong. Okay. So now I've swapped the number. So now what I will do is update the writer. I will increment it by 1. Then now I can say eventual pivot index is writer pointer. So if this eventual pivot index is exactly a k, I can return finish the recursion here. Otherwise, I will keep going. So and I have to make this k accessible here. And if eventual pivot index is less than k, I have to do the recursion positioning in the latter half. Otherwise, I will do it in the first half. Okay. So let me quickly check my code. So especially the partition method. Oh. So firstly, I will, pick the pivot index as the last element, which is high, index high. Then I will traverse the reader from low to high -1. And the writer start with index row. And now reader distance is this. Yep. And if the pivot distance is larger than the reader, I should say, if the reader distance is smaller than the pivot distance, I will swap reader number and writer number. Then increments the writer pointer by 1. And after the iteration, eventual pivot index should be as the writer pointer's index. Yep. Then according to the eventual pivot index, I do the partition recursively, or I just have to return. Okay. Wait, so k is what I'm looking for, and eventual pivot index is smaller than that. Yep, I just have to do it again recursively on the latter half. Good. Now I submit my code. Sorry, I'll comment this out. This isn't correct. So redo distances. So let me take a look what happens on the distance after, partitioning. So the order doesn't change. And for this, order hasn't changed. Hmm. So swapping hasn't. Oh, swapping actually changed, but ah. So now I remember the. Now I find why this is the problem. So as I said, if I'm looking for the second smallest, like k is equal to 2, then I have to wait until, I have to keep recursively doing partitioning until the eventual pivot index is k plus 1. So that's the problem here. If I'm looking for the first two elements, the pivot should be here, which is index 1 actually. So, sorry, this is k minus 1, Okay. Then also I have to give distance array as the first index, no first element. Hmm. So let me think with this example. So if k is 1, I keep positioning until eventual pivot index should be 0. And let me see. Okay, so firstly, when I call this with 0, 1, partition 0, 1, I get this. So pivot is chosen as 1, and but it seems like, you know, pivot number is 8, but number before pivot number 8, which is 10, is not smaller than pivot number. So probably the problem is within this range. Now I find the reason. In line 57, I have to move the writer pointer if I made a swap. Hmm. Oh, sorry. Also, I find one more mistake. So I have, as I said here in line 46, I have to swap writer, even show writer pointer's position, number, and number at index high. Okay, now it's accepted. Let me, you know, submit my code. Good. Now it's accepted. And a tip I can share more is, okay, so let me do the complex analysis first. So the time complexity should be O of n average, but in the worst case, it should be n squared. I will tell you why. So in this method, in this solution, I did the, partitioning recursively. And it totally depends which range to be recursively partitioned. It totally depends on the pivot numbers index. So if I pick, so say, if I take a look at all of them, and if I find that the pivot index I choose is almost at the center, then say I'm looking for the K, which is quite small. I have to do, scanning in the first half. And then, I mean, imagine that pivot is now almost at the center of the remaining range, and I will keep doing it. So in this case, the number of element I scanned so far is n plus n divided by 2 plus n divided by 4 and n divided by 8. And in total, it should be 2 times n. So on the average case, I have to scan in total 2n elements. So it would take overwhelming time. But in the worst case, so let's assume that numbers are sorted in ascending order. And every time in my implementation, I choose the last element as the pivot number. So every time the pivot number is exactly the last element in the chosen range, what happens is that the number of elements I have to scan and traverse is n plus n minus 1 plus n minus 2 plus n minus 3 plus blah, 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 1, which is n squared time complexity. So that's the worst case. But there is optimization to avoid this first time complexity as much as possible. There is, I pick the pivot number not from the last element, but randomly I choose from the remaining range. In that way, the probability that the pivot number is always positions at the last index of the remaining range is quite low. So I can avoid first time complexity n squared in most cases, unless I'm really unfortunate person. Okay. So let me add that optimization. So in this way, I pick the index of the pivot number, and then I swap it with the index high. And after that, as implemented, I will pick the pivot number as the element at index high. So in that way, actually, I chose the random number as the pivot number. Okay, so I run my code again. Oh, okay, I will submit it again. Good, now it's accepted. So this is the third solution, QuickSelect. Okay, so now I will introduce the fourth approach, which is the CountingSort. Good. So in the CountingSort, so I make use of the fact that square of distance is always, um, yeah, the integer. So maybe in this approach, I will experience time limit exceeded. But let me, explain how I can implement it. Then also, if time limit exceeds, then I will tell you why. So basically, what I can do is, again, I will create the array of the distances, just like I did before. Then what I will do from here is, I will, take a look at each distance, and I will create the huge array which stores, which has every slot for every distance square value. So it should be something like this. And what I should do is, for distance 10, there is one element. So I increment this position by 1. Then if I have distance square 8, I will increment this position by 1. Oh, wait. Actually, this doesn't work. Sorry. I was wrong. So CountingSort works only if I'm looking for the exactly case smallest element. Like, yeah. But that being said, let me quickly tell you how I can do it. Yeah. So what I can do is, oh, sorry, I should say, if I'd like to know which distance is the exactly case smallest one, then I can use this CountingSort. Yep. So wait a minute. Oh, sorry. I think I can actually use it on my second thought. Sorry. So let me continue my explanation. And if I find one more element whose distance square is 2, I will increment this throat by 1 and it becomes 2. And in that way, each element value represents number of the point whose distance square is this index 4. And in the end, I will do the linear scan for this element, and until the suffix sum is exactly k, which means that I've seen k element, I will keep looking it. And also, because I have to know which two elements are distance whereas k2, I will have the hash map, which represent distance to point. Yep, so this is it. With this approach, the time complexity should be assuming the max distance is, oh, I will just call it max distance. I will traverse each distance. Oh, sorry. But before, first thing I will do is iterate, taking a look at each point, and then I append it to the distance to points hash map and also to the distance to count, you know, um, list. Then it will take all of n, and after that I traverse these elements. So it should be up to max distance. In the case if k is unfortunately the number point. In that case, I have to take a look at all the points. Yeah, that's the worst case. For space complexity, actually for this list, distance to count list, I don't have to use this as the list, just the hash map works. So I will use the hash map and number of elements should be n. So this should be n. And also for in line 97, I have to put each point to the distance. I have to register each point to distance array. So it should be n again. So in total, it should take all of n space complexity. Okay. So let me start the implementation. For each point, I will register it to distance to count. Okay. So now I've built these two data structures. So the next thing I will do is I will take a look at distance square from 0 to the last element, biggest one. So while until I find k points, I will keep doing. So I will take a look if this current distance is inside of distance to count or maybe distance to points. And if it inside of the distance to count, I just have to take a look at distance to points. And I will get each point. Then I will append it to the found point in this way. Okay. Oh, but I have to make sure that in line 119, after appending, I have to break. Yep. So that I don't have to push any element into the found point anymore. And in the end, I will return found point. Okay. But one thing I have to take care is in line 115, every time I take a look at current distance is inside of the distance count, default dict. Even if it doesn't exist, new key is created just for accessing it, in my understanding. Wait, let me check and come back. Sorry, I was wrong. So please take a look at this example. So this is the, you know, where I tested in the IPython. So for default dict, if I just check if the key is inside of the default dictionary, this doesn't create a new key. So here I can't find, key 1. However, if I try to access it and if I get a default value from the default dict, then that key which I use for accessing is created in the default dict with the default value. So this implementation doesn't have any problem. Okay. Oh, and one more thing I can, update in my implementation is actually I don't need distance count because that information is included in distance to point. I delete it. Yeah. So this is it. Okay, so this totally depends on how much max distance is. If max distance is super large, it takes so much time. But in the case where max distance is not so large, but there's so many elements, in that case, this works quite good, especially compared with sorting algorithm or yeah, I think so. Okay, let me execute my code. Seems like I'm experiencing the infinite loop. Wait a minute. So let me debug it. So I print out distance to points. Ah, um, no, I think this is okay. This is, point to wrist. So in this case, I start current distance with 0. And every time in this iteration, oh, wait, here. I did continue here. That's a problem. So let me move this current distance incrementation first and start with -1. In this way, in 116, this current distance is always incremented. Hope this works. Good, accepted. So I will execute my code. Because xy is 10 to the power of 4. Oh, time limit exceeded. But anyway, so I think max distance square should be 10 to the power of 8 plus 10 to the power of 8 is 2 times 10 to the power of 8. And n is up to 10 to the power of 4. So in total, it should be less than 10 to the power of 9. So I think it's, yeah, maybe accepted. I thought so, but actually it isn't. Yeah, but anyway, I think it was good that I could introduce another solution, which works fine in some cases. Okay, so let me quickly wrap up my today's solution and question. So today's question, I solved the k-cross as point to origin, and I actually solved the similar questions like k smallest elements question in the read code, and I actually posted these videos. Yeah, but I solved this question again with 4 approaches, and I introduced first sorting, next MaxHeap of size k, and also I introduced QuickSelect, and finally I introduced CountingSort. Yep. So I think MaxHeap of size k is a good approach I can use basically, but QuickSelect works quite fine in some cases and most cases. So it also worth knowing and implementing, I thought. And for CountingSort, as I said, yeah, it also works fine in some cases, especially when max distance square is not so large. Yeah, so I think it's also interesting. Okay, thank you so much. I finished with this.